This is problem set 3, exercise 4. Now in this case, what we're going to do, we're going to use the configuration model in order to calculate the characteristic length, okay, this magnitude here, which is the average shortest path length of different networks, okay? The first one is going to be the scale-free network, this one over here. So this is what we're going to do now. Now, in this case, since we have the scale-free network, which is a constant times the power law. Now, in this case, since we have different regimes where the scale network, well, the scale-free works, let's say, depending on the exponent, we are going to do that. We are going to work this magnitude, okay, this value, for different ranges of beta, of the exponent beta. So the first thing that we are going to do is, well, I have to tell you that I'm not going to use exactly this expression, okay? So what the intention is to see how things work. Let's see how to see, what is the main, the most important value in this expression. So for example, if we have n, and here we have something that diverges, then I will have to take it into account. But if this is something that diverges with n, but this is something which is not, which is a finite number like this one, this I am going to neglect it. So I'm going to neglect all the terms that are on the lowest importance, okay? So that only the ones that are the most important are going to be the ones that I'm going to include, because this is just to know more or less the order of magnitude of this parameter. So we are going to start with what happens with when beta is greater than 3. So in this case, we have that the degree distribution has not only the average degree, but also the squared average degree, or the average of the squared of the degree. So this is how to compute the average degree, okay? Remember that we are going to use the approximation of the real, using the degree as if it was a continuous variable, as if it were a continuous variable. So I'm going to calculate it like this. So this is going to be k times the probability distribution, and the probability distribution is the constant times k to the minus beta differential of k. Now, I'm not really interested in how much this constant is, because it is a finite number. And remember that what I'm going to do, my intention is to get rid of, because this is a logarithm, so the logarithm of the product is the addition of the logarithms. So if it's something, if I have to compute the logarithm of a multiplication, I'm going to get rid afterwards of the small numbers. So as I was saying, this is what I obtain, okay? So this is c times the integral from k min to infinity of k to the minus beta plus 1, the differential of k, and this is going to be c times, since beta is greater than 3, then I can write k to the minus beta plus 1 minus beta plus 2, the plus 2 here, plus 2 divided by minus beta plus 2. Now evaluated at the bounds of this integral. So this is the result. Since we have that beta is greater than 3, this exponent here is negative, and therefore is going to converge when k goes to infinity. So I am only going to have the one that goes with k min, but with a minus sign, okay? So I am going to write this denominator with a chain, with the opposite sign. So this is the final result. This is going to be c over beta minus 2 times k to the k min, to the minus beta plus 2. Now this expression is also valid for beta greater than 2 for the average degree, but since I have to calculate also the average of the square degree, then that is why I'm being specific to this interval, okay, beta greater than 3. So the second part is going to be the integral of between k min and infinity of k squared times c times k to the minus beta, differential of k. And I'm going to skip this part, so I'm going to go to the final part, which is c times k to the minus beta plus 3 divided by minus beta plus 3. Again, evaluated at k min and infinity. So this is going to be now, in this case, since beta is greater than 3, again, the exponent is negative, so I'm going to have c divided by beta minus 3, k min to the power of minus beta plus 3. So now I'm going to use these two values in order to calculate the characteristic path length, okay, this expression here. Now, L is going to be, now I have, you can see here in this expression, I have this n minus 1, and all this, well, I have this minus 1, which I can neglect directly, okay? So now I have the, if I neglect this part, so this is like it didn't exist. So now I have this, the logarithm of the multiplication of n minus 1 times this part over here, sorry, this part over here. And now this part is finite. So we are going to, I mean, this is finite also for a finite network, because n is always a finite number, but this is going to be very large. Whereas these magnitudes are going to be not so large. So I can neglect them. Well, not neglect directly because it's multiplying, so I cannot neglect, but since I have the logarithm of the multiplication, then this is going to be the logarithm, the addition of the logarithm. So this is going to be the logarithm of n minus 1 plus the logarithm of the other part. Well, and this is not unequal. Remember that I'm interested here in the approximation. So this is going to be the logarithm of the average of k squared minus twice the average of k divided by average of k, everything squared, divided by the logarithm of minus blah blah. Okay, so now is when I can neglect terms, okay, because this term, which is going to be very small compared to this one when n is very large, what I can do is to neglect. And in the end, we are going to have something which is proportional to this thing here. And instead of n minus 1, of course, I'm going to write only logarithm of n. So in the end, what I'm going to have is that instead of this equal sign, I write this symbol, okay, which is something which is of the same order, of that goes like something proportional to the logarithm of n. Okay, so this is in the end how this magnitude is going to behave. So for the same degree distribution, the same scale-free degree distribution, what we have is that as n gets larger, okay, as the network, the number of nodes increases, then we are going to have that this average distance is going to increase also, with like, it's going to go like with a logarithm. That's the idea. Okay, and this is the result for a specific range of beta, which is beta greater than 3. Now we are going to go to the second region, which is beta equal to 3. So let's see what happens when beta is equal to 3. Now, in this case, we have that, well, the first part here for this average is going to be exactly the same, but now for the second part, here we're going to have that this is going to be k to the minus 3 times k squared, so we are going to have a k to the minus 1. So the integral is going to be a logarithm. That's the idea. So the integral is going to be a logarithm. Now we have k squared, the average of k squared is going to be the integral from k min. And since it is a logarithm, it's going to diverge. So I have to use now the k max approximation, okay? So I have to use the k max. And then I'm going to use that, and this is in general, okay? I'm going to use that k max goes like k min times n to the power of 1 minus over beta minus 1. So this is going to be the expression that I'm going to use. This is it, this one. And now, as I was saying, this is c times k to the minus 1, differential of k. Okay, so this is c times the logarithm of k max divided by k min, which is in the end the logarithm of n to the power of 1 over beta minus 1, or c times 1 over beta minus 1, the logarithm of n. So this is the result. So now k, the average of k squared, this is going to go like the logarithm of n, a multiple of the logarithm of n. And we are going to use this in this expression. So I'm going to use the same expression here, okay, where I already neglected the minus 1 here in the numerator, but now I'm going, and this is finite, so this part I can neglect. So what I'm going to do is, well, I'm going to do the following. I'm going to rewrite that expression. So I have that L is going to go like, well, first of all, the logarithm of n minus 1, which is going to be the logarithm of n, plus the logarithm of the quotient, which is going to be the subtraction of these logarithms, okay, the logarithm of k squared minus twice average k, minus the logarithm of, well, I can write logarithm of the average of k, and this is over the logarithm of the average of k squared minus the average of k minus the logarithm of the average of k. And now I can neglect terms. Okay, when I write it like this, I can neglect terms. So the first terms that I'm going to neglect are this one and this other one, because remember that this is going to be large. Okay, so this is going to go like the logarithm of n, which diverges when n is large, but this is constant. This only depends on k min. So I'm going to neglect this part and also this other part here. And let's see what happens. So this is going to go like, so first of all, I'm neglecting the parts that are most obvious, okay, most obvious, but then let's see what happens after that. Okay, so this is what I have here, minus twice k divided by the logarithm of and now what I'm going to do, now I can do the same with this part. Okay, so I'm going to neglect these two terms, because remember that this goes like this. Okay, this goes with the logarithm of n. So here I have that L is going like the logarithm of n plus the logarithm of some constant, and this is the part where I can neglect. Okay, so this is going to be c over beta minus 1 times n, it's times the logarithm of n, and this is over c over beta minus 1, the logarithm of n. So remember that in this case, what I did was to neglect these two terms and also to substitute the value of the average of k squared. That's what I just did. And now, since I have the logarithm of this multiplication, I can write this as the addition of the logarithms, but this is going to be a very small number. So again, guess what? Yes, I'm going to neglect. So this is what I have, plus the logarithm of n divided by the logarithm of n, plus some things upstairs and some things downstairs. But the thing is that this is going to be much smaller than this part over here. So again, I'm going to neglect, even though this is going to diverge, but it's going to diverge much more slowly than this other part here. So the largest, the fastest term is going to be the one with the logarithm. So this is going to go like the logarithm divided by the logarithm of n. And this is going this is the behavior of this characteristic path length in the case of this when beta is equal to 3. That's the point. And finally, let's see what happens when beta is between 2 and 3. Okay, so when beta is between 2 and 3, still the average degree is going to converge, but the average of the square degree is not going to converge. Not like a logarithm, but this time like a power. So it's going to be much faster, the divergence. So now the average of k squared is going to be c times the integral from k min. I also have to use the k max trick, because if not, this is going to diverge of k squared to minus beta, differential of k. This is equal to c over 3 minus beta. And remember that now I have k to the 3 minus beta evaluated at k min and k max, which is going to be c over 3 minus beta. Remember that this is a negative number now, okay? So 3 minus beta, sorry, this is a positive number. So here I have k max to the power of 3 minus beta minus k min to the power of 3 minus beta. Again, for sizes, okay, to see what is large and what is small, this is going to be very, very small, so I can neglect this compared to this value here, okay, and that's it. So what I'm going to do now is to substitute the expression of this part here, okay. So now I'm going to write that k max. This is going to be equal to c over 3 minus beta, and now I'm going to substitute, okay? So this is going to be, when I substitute, I obtain k min to the 3 minus beta, and then n to the power of 3 minus beta over beta minus 1, and then a minus 1, okay? This is what you obtain when you do this, when you substitute this expression and you do the power of this expression to the power of 3 minus beta. So I have a 3 minus beta here and also a 3 minus beta here. That's the idea. And afterwards you take common factor, this k min to the power of 3 minus beta. So this is the final expression. As you can see, as you probably think what I'm going to do, I'm going to keep only this part. I'm going to neglect this part. And this part, when I do the logarithms, is going to disappear also. Okay, so in the end, what I have is that L is going to go like the logarithm of n plus the logarithm of, as I say, this part is going to just vanish, okay? I'm going to neglect that part. So this is going to be like the logarithm of n to the power of 3 minus beta divided by beta minus 1 plus some smaller quantities, much smaller quantities, and this is over the logarithm again of this k max, which is going to be again like something like this. And the things that I don't write here, this means that this is not important, okay? I can neglect these terms. So this, now remember that this is the logarithm of a power. So I can write this as the logarithm of n plus this power, the logarithm of n divided by 3 minus beta divided by beta minus 1, the logarithm of n, plus some other things which are not so important. And in the end, you can see that we can get rid of all these logarithms, and in the end we are going to obtain something which is constant. Okay, it's something that doesn't depend on n. The value of the constant is not so important. The most important thing in this case is that the result is not going to depend very much on n, when for n large enough, okay? So it doesn't matter if we are talking about a network of size n or twice n or 10 times n or 1,000 times n, because the result is going to be more or less the same, which is quite interesting, by the way, because this is telling me the average distance between the nodes in the network. So it's interesting that in this regime And also assuming, be careful, because we are assuming that we are in the configuration model where there are no degree correlations, we obtain that this is constant. There are some works where they assume that they have assortativeness or assortativity, and in that case they obtain something which is slightly different. So in this case, instead of constant, it goes like the logarithm of the logarithm of n, which is much smaller, much slower. Okay, so that's another thing, and that's it.